This is Physics 1060 Descriptive Astronomy Lecture 13. Today we're going to be talking through Chapter 16. Star clusters. Some of the Milky Way stars are gravitationally bound together in groups called star clusters. There are two types of star clusters, open clusters and globular clusters. Open clusters contain up to a few hundred members in a volume typically 7 to 20 light years across. The Pleiades, or the Seven Sisters it's also called, is an excellent example of an open cluster. They're also called galactic clusters since most lie in the galactic disk. They're formed when interstellar gas clouds are compressed and collapse upon entering the Milky Way's spiral arms. About 20,000 open clusters currently exist, many of them obscured by dust in the galactic disk. Within spiral arms, very young stars may group together in a loose association a few hundred light years across. Single large open clusters near their center, and the birthing gas and dust is still present. After hundreds of millions of years, the stars gradually leave and the cluster dissipates. Here are some pictures of different open clusters. The Pleiades, we said, is one example. There's some other ones, M67. M just refers to a certain catalog, the Messier catalog, object number 67. Or NGC is the New General Catalog, object number 3293. They're just books that contain locations of different objects and describe them. These are all open clusters. Globular clusters contain far more stars than an open cluster, from a few 100,000 to several million per cluster. They have large radii, maybe 40 to 60 light years across, and a strong gravity pulls the stars into a ball denser than that found in open stars. About 150 to 200 globular clusters outline the halo and bulge of the Milky Way. Here are two pictures of globular clusters. This is M13, so 40 to 60 light years across, but it might have 1 million stars in it. They're really brilliant objects and a lot of fun to see in a telescope. So open and globular clusters reflect the properties of population 1 and population 2 stars. Open clusters are generally population 1, globular clusters are population 2. So in order to understand clusters, we must first discuss the types of stars around us in ways other than temperature and luminosity. So we can take a stellar census. It counts that list all the known stars of a given type in a region of space is called a stellar census. All star types are represented in our galaxy. By analyzing the relative number of stars of each type, we can deduce the galaxy's history. Brings us to something called the mass function. From a stellar census, one can derive the number of stars of each mass, typically known as the mass function. Mass, as you know, determines the life cycle of a star. The evolution of our galaxy will then depend on how many stars of each type it contains. A galaxy with only massive stars will evolve quickly, and how fast each type is created. Fast creation will deplete gas resources quickly. So we get some results from our galaxy. Dividing the number of stars in our galaxy by its age gives a star creation rate of about 3 to 5 stars per year. The most numerous stars tend to be dim, cool red dwarfs, about a half solar mass. The average mass for stars in our galaxy is about 1 solar mass. Stars more massive than 100 solar masses are rare. Current research suggests that brown dwarfs, or failed stars, of mass less than 0.08 solar masses, are more numerous than ordinary stars. It's important to be aware of selection effects when interpreting data. Absence of evidence is not evidence of absence. In other words, there may be things out there we just cannot see. So the two stellar populations, population 1 stars, are generally young, 1 million to 1 billion years old. Their color is blue generally, and they are located in the disk and really concentrated in the spiral arms of the galaxy. Their orbit is approximately circular in the disk of the galaxy, and they have a high heavy element content similar to that of the Sun. Population 2 stars are old, about 10 to the 10th years, or 10 billion years. The color is red, and their location is out in the halo of the galaxy. I think of the galaxy as a a basketball with most everything in a line that goes right through the center, so the spiral. But there's some stuff in this spherical region. That's called the halo. The bulge is the center bulge here. That's the location of population 2 stars. And their orbits can go way out and plunge through the disk. And they have very low heavy element content, 100 to 1,000 times less heavy elements than in the Sun. Now, division of stars into just 2 groups can be an oversimplification. Actually, the Sun doesn't really fit into either category, but it's typically thought of as a population 1 star. So that inspires creating subgroups. Subdivide each population into extreme and intermediate, or oldest population, sometimes used for stars like the Sun. Now, the 2 populations show that star formation has not occurred continuously. Population 2 stars formed in a major burst at the galaxy's birth during the initial collapse of our universe. Population 1 stars formed much later and are still forming today. Population 1 stars are used to map the spiral arms and vicinity around the Sun. Now, astronomers assume that when you see a cluster of stars, they were all formed at about the same time. There are several reasons for believing this. High-mass stars, the OB stars, which have to be young since they evolve so fast, are usually found in groups and clusters. And stars ought to form in groups since large interstellar clouds are more unstable than small ones. It's theoretically very unlikely for hundreds of stars to come together to form a new cluster unless they were born that way. And the HR diagrams of clusters indicate that they all have a definite age. The stars in a cluster have a wide variety of masses. If they were born at the same time, they must be at different evolutionary stages. And we can see this by plotting an HR diagram for all the stars in one particular cluster. So, for example, this is the HR diagram of the stars in cluster NGC 2264. Note that most of the stars are above the main sequence, as predicted by a young cluster. All these stars have yet to get to the main sequence. The higher mass ones are already on the main sequence, and the even higher mass ones may have already burned up all of its hydrogen and are starting off into the giant phase. This is a picture of that same cluster. Now remember, different stars, depending on their mass, take different amount of time to reach the main sequence. Small mass ones may take up to 10 million years, or large mass ones only 160,000 years. So after a cluster is born, more or less at the same time, the high mass stars go through their main sequence lives more quickly than the low mass stars. So the overall appearance of the HR diagram for the cluster changes. At 1 million years, stars in this part of the HR diagram are still protostars. They haven't reached the main sequence. Whereas the supermassive ones have already become a star, lived out their lives, and are in their death throes. And so by looking then at the turning off point of where stars are dying, I could tell the age of a star cluster. So the astronomers can use the HR diagrams to estimate the time since the cluster was formed. This is one of the very few ways there is to estimating the ages of stars. In M67, the globular cluster we were looking at early, the turnoff point is relatively far down, so this means it's a very old cluster. Or the Pleiades, it's kind of a medium age, or the one we're looking at is a very young cluster. Now the reason for the difference between the two types of cluster is that globular clusters were formed when the galaxy was young, and not many metals had been made inside stars yet. The open clusters were made more recently, when the interstellar material was richer in metals. The final difference between the two types of the cluster is their location in the galaxy, and we'll return to this later. Now, except for globular clusters, which can hold themselves together indefinitely, clusters eventually break up and drift apart. And one reason for this is the differential rotation of the galaxy, which we'll talk about later. Our Sun was probably a member of a cluster when it was young, but we cannot identify any of its siblings now. Now the Milky Way is the name given to our own galaxy. It's also sometimes referred to as the galaxy with a capital G. In this section, we're going to try to understand how stars and other material are distributed around the sky. So the pale band of light, spangled with stars stretching across the sky, is the Milky Way, a swath of light named by the ancient Greeks. In the 17th century, Galileo showed the Milky Way is actually millions of stars too dim to see individually. Today, we know the Milky Way is a slow revolving disk of stars, a galaxy. We also know today that the Milky Way is filled with stars of various sizes, many of them found in clusters and clouds of gas and dust. Now, the uniform distribution of stars in a band across the sky led Thomas Wright, Immanuel Kant, and William Herschel in the 18th century to suggest the Milky Way is a disk distribution of stars with the sun near the center. If the Milky Way was spherical, stars would be uniform regardless of which direction we looked. But because the Milky Way is a disk, we see stars when we look in certain directions, and very few when we look up and down. William Herschel's sketch of the Milky Way from 1748 is shown here. The sketch led Herschel and others to believe the Milky Way was disc-shaped, which was correct, and that the solar system was near the center of that disk, the position of the yellow dot here, which was incorrect. Now, correcting for dust effects and variable star types, astronomers conclude the disk has a 30 kiloparsec diameter with the Sun 2/3 from the center. 30 kiloparsecs is approximately 50,000 light years. The discovery that nearly all disk-shaped galaxies have spiral arms implied the Milky Way has spiral arms also. So, looking at the structure of the Milky Way, the first thing I want to talk about is the disk. Spiral arm distribution of stars, gas, and dust within a diameter of about 100,000 light years, and a plane tilted with respect to the Earth's orbit around the Sun. Differential rotation with all objects circling in the same direction. 240 million year period at 220 kilometers per second at the Sun's orbit, which is about 8.5 kiloparsecs away from the center of the galaxy. Now, there's a high density of stars near the center, about 10 million stars per cubic light year, to low density further out, about a 3,000th of a star per cubic light year at the distance of the Sun. And dust and gas is nearly 15% of the disk's mass. Most of the galaxy is hidden from the Earth due to dust obscuring, including the central nucleus, with its dense swarm of stars, and gas, in which a massive black hole also may reside. Radio and infrared telescopes can see the entire galaxy. Radio observations suggest larger warped disk of gas out to about nearly 40 kiloparsecs. The halo, again, is a roughly spherical region with the disk embedded in the center. It contains mainly old stars and globular clusters. Large amounts of dark matter may also be present. Well, what is dark matter? Well, it's stuff that exists out there that we're going to talk about more, that we know is there because of gravity, but we can't see it, hence it's dark. And the bulge of the galaxy is a flattened collection of stars surrounding the core of the galaxy. It's about 1/3 of the diameter of the galaxy. From its rotation and effects on nearby galaxies, the mass of the Milky Way is about 2 × 10⁻² solar masses. From large differences between this mass and what we can actually see in terms of stars, astronomers conclude the Milky Way is embedded in a vast halo of material that emits no radiation at any wavelength, called dark matter. Assuming the average star has a mass similar to that of the Sun, then based on the Milky Way's mass, there are roughly 100 billion stars in the Milky Way. Using stellar aging techniques, astronomers had estimated the galaxy's most ancient stars to be about 15 billion years old. More recent model calculations and observations suggest old star ages are more like 13 billion years. A rough estimate of the Milky Way is then between 13 and 15 billion years old. The galaxy is held together entirely by gravity. Each star orbits around the center of the galaxy, and all the stars in the disk move in the same direction. Stars in the halo have randomly oriented orbits, but in the disk, we're all moving in the same direction. Now, stars at different distances from the center of the galaxy move at different speeds, just like planets at different distances from the sun move at different speeds. That process is called differential rotation. And it's this that leads to the mixing up of stars and the breaking up of star clusters. A star cluster forms. Ones that are slightly closer to the galactic center are moving at a faster pace around, and eventually they get strung out into spiral arms, and they separate. Since we know the period and size of the sun's orbit around the center of the galaxy, we can use Newton's law of gravity to determine the mass of the Milky Way. There are about 10 to the 11th, or 100 billion solar masses within the radius of the sun, plus some more out. Most of this is stars. About 10 to 15% is interstellar matter. Since the average mass of a star is about a half solar mass, there must be about 2 times 10 to the 11th stars in our galaxy. Again, we only see a small fraction of them because of extinction. Now, what about the center of the galaxy? Because it's not observable in the visible, astronomers must rely on radio, infrared, X-ray, and gamma ray observations. At a distance of 3 kiloparsecs from the center, an arc of cold hydrogen sweeps outwards at speeds exceeding 100 kilometers per second. A giant swarm of stars, packed in at millions of stars per cubic light year, are arranged in an elongated structure about 1,000 light years across. Some energetic event, perhaps a supernova explosion, violently disturbed the center in the not-too-distant past. Deep within the core lies an incredibly small, say 10 astronomical units in diameter, radio source, known as Sagittarius A. A 10 to the 6, or 1 million solar mass black hole may occupy the very center of the galaxy, although other explanations have been given of what this incredibly small radio source could be. So if we plot the path of stars near the galactic center, we see they're all moving around in elliptical orbits around some incredibly small, incredibly massive object at the center. How did the galaxy form? Well, forming galaxies is still a major unsolved problem. Currently, it's thought that galaxies formed a lot like stars formed, but just on a larger scale. So we begin with a 1,000,000 light-year cloud with 100 billion solar masses of material, and the cloud gravitationally collapses and breaks up into stars. Evidence for this galaxy formation process can be found in the population 1 and 2 stars. So the proto-Milky Way galaxy was a giant cloud of pure hydrogen and helium. The existence of old population 2 stars with very little heavy elements suggests they formed at the onset of the collapse, and as they did so, they dropped out of the gas collapse. So a slowly rotating pregalactic cloud of pure hydrogen and helium begins to collapse under its own gravity. Some stars form. The massive population 2 stars exploded early on, seeding the galaxy with heavy elements. By the time the cloud collapsed into a disk, it was rich enough in heavy elements to generate the population 1 stars we see today. So, stars form in the disk, higher mass stars in the halo die, leaving only low mass red stars in the halo behind. Now, we can do a computer simulation of galactic formation, and what we do is we put essentially a uniform hydrogen cloud in a giant disk, and we look at what happens given a slight rotation. And what comes out of the computer afterwards looks exactly like the spiral galaxies we see today. That's it for today's lecture.